6.4/5, we're going to talk about glancing collisions, which is collisions in 2 dimensions, and we're going to talk about rockets, which with the rocket equation, it is really easier if you just use like the equation for it, or look at the units, because it's like mass per second. So look at your units to try to figure out what you're using, like to solve for a velocity or something like that. It's a lot easier that way. And just look at like when the rocket takes off to the time after. Don't really worry about as it goes, because you can easily do like an integral or something like that when you get up into the upper level physics. They're not going to ask that of you yet, not in this level anyways. So we're going to look at those 2-dimensional collisions and those rate of fuel usage. So glancing collisions. These glancing collisions, this means that one object hits another object, and depending on how it hits it, think of like pool balls when you just like nick the edge of it or something, it's going to go off in not the straight direction, right? You're trying to get it to go to the side, or maybe you're not and you're just a lousy shot like me. So that means that whatever angle it hit with, it's going to have some x and some y momentum. Or maybe it won't. Maybe it'll only have an x, and then the 2 balls in the end need to even them out so that if they do have an x and a y with one of them, this one's going to balance the x and y in the other, so that it cancels, and in the end it should end up that the momentum is basically all in the x because the y's cancel. So you're looking at the same collision equations that you used, the same conservation of momentum, just with I hats in the x direction and j hats in the y direction. Which means more vectors. Okay, are we ready? So here's a picture of a glancing collision. You can see that the momentum initially only starts out in the x direction. So these two things are going to have the same, so some part of this vector, you can see about half of it goes into this one and this half. Now it doesn't have to be half. This one could end up being slower in the x, as long as both of these x vectors add up to the original x vector. And you can see the y vectors will end up canceling each other out if they were added together. So one is up and one is down. So you'll still end up with the same initial momentum, even though these ones have some sort of y. A lot of the times when you're talking about 2-dimensional collision equations, you'll also talk about explosions. So initially it'll have like a firework, it has initial momentum and then it splits into 2 or something like that. Or it has 0 momentum in the initial because it's just like sitting there like a bomb, and then it explodes into like 3 pieces, or it could be any number of pieces. It could be 10 pieces. But you see that if you add up the momentums of all of those, because of the direction, they'll end up canceling them out. So all of the initial momentum was 0, and in the end, the momentums are all over the place, but they all add up to equal that initial 0. Unfortunately, I really do need to move on here, so I'm going to move to the next slide. If the collision is elastic, which it'll tell you if it's elastic or not, it's not something you can really assume unless you get super stuck and be like, okay, do I have to assume this? And maybe you could. But most of the time it'll tell you, and that means you can use the conservation of kinetic energy. Since it's a scalar, you don't have to worry about the x and y direction. You would just look at the magnitudes of velocity. So if you do know for like V1 final, it has an x and a y, you're going to use the magnitude formula here for the vector to put the velocity in. So these ones you have to use the full magnitude, not broken down into components, which is a little annoying sometimes because you have to have components for the other one, but this one you don't. And so you end up doing the velocities like 3 different times, x, y, and magnitude. I know that that's annoying, but sometimes it will help you really solve the problem. Given the 3 equations that we have here, the conservation of momentum for x, for y, and for the kinetic energy, you can solve like the velocity of 1 and 2 and the angle for one of them if you know that the final angle of this one is that. So that kind of helps a little bit. So when you're solving for these 2-dimensional collisions, the first thing you want to do is kind of set up a coordinate system. If your object is heading in one direction, which usually is just like one object and it hits another object that's at rest, even if it's coming in at an angle like this, that doesn't really matter. So if it hits it as like a glancing collision like this, you could just say that your coordinate system just tilts it a little bit. So that way, when you're dealing with the after collision, your initial one is only in like the x direction or something. So that's something that you can do. A lot of times it won't really give you a picture, or if it does give you the picture, it would be like a nice, even, straight one hitting an object, and then it splits here and here like this. That's usually what your pictures will look like. But even if it's coming in at some sort of angle, that initial angle doesn't really matter as long as it's compared to that, but usually it will be. Something like that, and that way. That will just kind of help simplify your formulas a little bit, so you don't start out with an x and a y, but just an x, and then your ending will be an x and a y. So you don't have to do x, y, x, y. You just have to do x and then x, y. Just trying to help you a little bit. Now, it'll still work. It'll still work if you did your coordinate system like normal. It will, but it's just that much more calculation. They do say to sketch the diagram. That does help. Notice that I have a couple of diagrams up here. Sometimes it's helpful. Sometimes, it's like, I can do it without it because you're just looking at the numbers, and that's fine. If you do draw a sketch, it would be easier if you had, mass labeled and velocities labeled for each of them, at least when you're plugging in. You can still do this with a grid, too. After you've drawn your picture, you'll write the conservation of momentum for the x, for the y, and then solve. Solve for your unknowns. Maybe you don't know v final, maybe you don't know v final 1 and theta 1, theta final 1. So since you have the x and the y equations, you have 2 different equations. You're going to have probably 2 different variables that you need to solve for, so you'll have to substitute in the end, which is nice. I mean, not nice, but ways you can solve it. Okay, some more weights. So you can use the conservation of energy if it's elastic, but it has to tell you that it's elastic. And this, if that's true, if the conservation of energy is true, and you can use that in this case, you can actually have three unknowns because you'll have three equations. You'll have the x, the y for momentum, and then the kinetic energy. This one, you may have to use the quadratic if you do it, but there's that. V1 initial minus V2 initial equals negative V1 final minus V2 final or something like that. You can use that equation instead of using this kinetic energy equals this kinetic energy. It's the same equation, it's just simplified. So that one is a lot easier to solve than doing this and trying to do the quadratic for it. Once you've set up your equations, you want to solve for the unknowns. You can do it simultaneously by either substituting or having the two equations. There's one more way of doing it, especially since you have vectors. A lot of times you're going to get your x equation all the way down to some sort of number equals v cosine theta. Well, v cosine theta is the I hat, so you already have the component for it. And same thing, you'd end up with like 4v sine theta. 4 equals v sine theta. That, since it's v sine theta, is just the j hat. So you can find magnitude and direction just using your normal vector equations. All right, so now let's talk about rockets. Do a little rocket science here, at least rocket math. Rockets depend on the law of conservation of momentum because they're ejecting fuel. So they're ejecting mass in one direction, and that propels the rocket in the opposite direction. Since mass is ejected not all at once, but over an amount of time, they usually do like a fuel rate, so kilograms per second. And this is what speeds up the rocket. Sorry, what?
What just happened?
Someone walked out the door.
Okay.
It's okay. Not a big deal. So since mass is continuously being ejected, the velocity of the rocket continues to increase. That means the rocket is getting faster and faster and faster. So the more time that goes by, the more amount of mass that goes out, meaning that the faster that the rocket starts to go. So that's like when they're saying an engine burn or anything like that. It's going to increase the velocity of the rocket or change its velocity, right? Change its direction. So the rocket's accelerated as the exhaust gases are expelled, and that is called thrust. It is a representation, it represents the inverse of the inelastic collision. So if you think about an inelastic collision, like a perfectly inelastic one, two objects hit and stick together. So this is kind of backwards. They start out as one object, and then they split apart.
So it's somewhat like solving for one of our problems we had was the rail car with the machine gun on it. It's basically like that.
Mm-hmm. Except for instead of, nope, it's exactly like that. Yep. So momentum's conserved. Sometimes kinetic energy is conserved. In this case, it's actually increased because your fuel is, ignited and increases its energy. So as it's heated up, it's flying faster and faster, so it has a higher kinetic energy. So you actually increase your energy because you have some sort of chemical and combustion going on that's increasing mechanical kinetic energy, which is kind of neat. Energy is Okay, so here is some helpful little equations that hopefully won't confuse you. They're a little confusing. But your mass, your initial mass, is the mass of the rocket plus the change in mass delta M, which is going to be the mass of the fuel burned. And your initial velocity is going to end up being v. So your initial momentum is the mass of the rocket plus that of the fuel times velocity. Which that one seems pretty straightforward. Where it gets tricky is when it says it's been 10 seconds and not all the fuel is used yet. How much fuel is left or something. So you have to account for the stuff that's lost, move it to the other side of the equation, plus the stuff that you have, plus the rocket. So, you know, if you can keep track of it, it's not too bad. And also, if you're in calculus or you're planning on becoming a physics major, you can, integrate and do that kind of stuff as you'll have a function of time as the mass leaves the rocket. This delta M sets you up for derivatives and intervals. So after or during, depending on when you're looking at it, when your final position is, the rocket's mass is still M, hasn't changed. The mass of fuel, delta M, is being ejected, and the rocket's speed has increased to v plus delta v. So it has its initial velocity plus that change in velocity that it had due to the mass. And this mass, this delta M, doesn't have to all escape. Some of the delta M could still be here because it would be like halfway through its burn or something like that. But basically, as delta M moves from the rocket into here, from the initial side to the final side, the velocity, the delta V, is going to increase, and the initial velocity will stay the same. It's going to go this way and this way. We'll only talk about these rockets in one dimension. We won't talk about them in two dimensions. I see all blue cups. Is that right? Okay. So here is a fancy equation for you to use when it comes to rocket propulsion. V final minus V initial. There's your delta V. It's going to be equal to VE. I believe that is the velocity after everything has been expelled, or as it's being expelled. And that's equal to the natural log, ln, of the initial mass over the final mass, where the initial mass is going to be the rocket plus the fuel, and the final mass will just be the rocket plus anything that's left. So you're really only looking at the rocket in this equation. This is the exhaust. So I believe that this is the velocity of the rocket initially, rocket finally, and this is the velocity of the exhaust. Kind of nasty, huh? Why does rocket science have to be so hard? Okay, here's another equation for thrust, force. Remember, F equals ma. So if that is true, you can break A into delta V over delta T. But since we actually have a velocity of the exhaust that stays pretty constant, the delta M is changing, right? The mass of the fuel is changing. So we take this delta from the V and move it over to the M since it's what's changing. So it's actually a function of mass now. You won't have too many of these, just letting you know, to expose you to it in case you decide to work in NASA. And then after this, I believe I just have a bunch of clicker questions. So should be too bad. Okay, here is question 1. A 90-kilogram halfback running north with, and I believe a halfback is some sort of football player, just so you know. It's running north with a speed of 10 meters per second, is tackled by a 120-kilogram opponent running south at 4 meters per second. The collision is perfectly inelastic. Compute the velocity of the two players just after the tackle. So again, I think we're talking about some sort of sports ball here.
So is he like beside 2 quarterbacks?
That's a good question. I would love to actually ask the football player that.
Too bad we have no losing here.
Yeah, not in this class. Not going to happen. I have some very smart football players, but they're usually too busy to take an AP class because of football. So it's not that they couldn't, they just, well, it's not that they couldn't do it, they just don't have the time. Okay, so I would love to use the grid on this, but I feel like if I use the grid, I'm going to have to start doing like an X and a Y thing, and my grid is going to get out of control.
I don't think you need to, because they're just heading in opposite directions. So.
Oh, one's north and one's south. Yeah, you're right. I guess I was trying to get one west and one south, but whatever. All right. Never mind. It's much easier than I thought it was. What do you guys do? Okay. We'll do the grid. All right. I was hoping that this was a two-dimensional equation, and I thought it was when I put it in here, but it is not. So it's much easier than I thought it was going to be. Here's our grid. Initial, final, final. And at the top, MVP, right, for momentum, not most valuable player. Okay, so we have the 90-kilogram halfback and the 120-kilogram, whatever the other thing is, opponent. Initially at 10 meters per second running north, and the other one is initially at 4 meters per second running south. So you just have to put in your signs there. They then tackle each other and stick together because it's a perfectly inelastic collision, so their finals are the same finals. So then we're going to use some math to go 900. And then we're going to go this plus this equals this plus this. And solve for your unknown. Right? Not too bad, right? You can figure it out. The next one is a two-dimensional problem. Yay. I didn't get that answer. Did I make a mistake? Divided by 90 plus 120 is 210, right? Yep. Oh, there we go. I don't know what I did before, but that worked. Okay, are we ready to 6, 8, 10, 11, and some 1%? There we go. Okay, I got 2 meters per second north. Is that what you guys got?
Yeah.
Ooh. All right. Because the answer should have been positive. Okay. Question 2, this one is actually truly a two-dimensional question. We are going to do this. There we go. Okay. Let us get a new board here. So it says a baseball infielder of mass 75 kilograms jumps up with a velocity of 3 meters per second. So we have a velocity going up. And it catches a 0.15 kilogram baseball moving horizontally, so we have the x direction there, at 50 meters per second. At the following, which is the closest to the final momentum of the system of the infielder. So you're looking at the final momentum, just the magnitude of that, since it didn't really say direction isn't in the answer. And you can't just add 3 to 50 because 3 is going up and 50 is going to the side. Because the masses are different. So let's look at the stuff in the x direction. The initial mass of the infielder is 75. I'm just doing mv plus mv equals mv plus mv. Well, they're going to be stuck together. So this is mv, so 3. And this is the, this is the j hat direction. That's not going to work. Let's do this. Of course, I did not erase it correctly. There we go. 75 times 3 j hat. There we go. That's much better. Plus the baseball, 0.150. And this is again mv. This is going to be 50, and it's horizontal. So this is your I hat. This is equal to m plus mv, right? Because they're stuck together. So this will be the 75 plus 0.50 vf, and it's going to have some j hat and some I hat. We don't know what it's going to be. So if I break this up a little bit more, since I can't really solve it like this, this is stuck here. We're going to have, I know what we can do. We can kind of solve it a little bit. This is going to be 150, 300. It's been a while since I saw one of these. I have to really think about it. 225 j hat plus, that's not right, 7.5 I hat equals 75.150 VF. I'm solving for VF here, so 225 divided by 75.150 gives me 2.99 j hat plus 7.5 divided by 7.1, giving me 0.0998. So we'll just round it up to 1. I'll do that. This is I hat, sorry. Equals VF. Now you want to find the magnitude of this VF. You're going to use the magnitude formula, where you go x squared plus y squared. And that should be...
Students, it's time for your afternoon announcements. Order your yearbook today.
Oh, it's looking for momentum. So take this VF, VF,
or credit card at yearbookforever.com. All Powder Puff players and coaches, there will be practice today.
Because it's looking for the momentum final. I just found the velocity final. Sorry about that. If you had just taken this right here.
Students, don't forget this week is Red Ribbon Week.
It's asking for P, not V.
Team
I saw
Up
for V.
Against Drugs. Wear your favorite team jersey to school. Don't forget to check the list in the cafeteria and the dean's office.